Hi guys, welcome back to the CS Classroom. What we're going to do today is we're going to cover linked lists and binary search trees. Now this is part 3 of the series on abstract data structures, and after covering that we'll probably do a few review questions surrounding those topics. Before continuing, I also wanted to give you guys a few channel updates. So a lot of you guys have been asking about option A. Option A is in progress, and I expect to have that out this weekend. Additionally, if you haven't yet, please check the description for cram guides. Those are guides I put together that takes all the information required to pass the exam and puts it in a concise and easy to understand form. I think it's really great for revising. And for those of you who already purchased the cram guides, there have been some minor updates about the HL and SL guides, so be sure to check those out. That being said, let's go ahead and let's get started. Now the first topic we're going to work on is going to be linked lists. So we're going to cover 3 types of linked lists today: singly linked, doubly linked, and circular linked. These may also be called single linked and double linked rather than having the Y. And these are all the different components that are involved in those linked lists. Now let's take a look at how to draw these, because that's going to be a task that you're going to have to do on the IB Computer Science exam. Specifically the HL exam, of course. And furthermore, once we've done that, we're also going to look at some basic tasks. But let's get into how to draw them first. Okay, so let's start with a singly linked list. Now, as we said before, every single linked list has 4 components. It has a head, it has a tail, it has pointers, and it has nodes. Now, before getting started, what's important to understand is that a singly linked list is basically a collection from the SL curriculum. And as we go through how this works, you'll see why that's the case. So let's just start with a very simple singly linked list with 3 nodes. Now, each node has 2 components to it. It has an information field, we'll just say info field for short, and it has a pointer. Now this is a way for us to store data. This is a data structure, and the info field is going to contain any data we want to store, which in this case is just going to be an integer. So let's put 5 in there, for example. So that's going to be our first node. We'll get to what the pointer does here in a second, but let's say we have a second node. Of course, that one contains the same components, and in its info field we have, let's say, -9. Now, what the role of the pointer is to point us to the information field of the next node in our linked list. So whenever whenever a program accesses this pointer right here, that essentially leads us to another memory address. A memory address looking something like this. So when we access the pointer, it takes us to the next node in our linked list. Now this means, just as how we explain a collection, all of our nodes can be spread out throughout the memory, and we go from one node or one piece of information to the other using pointers. So we've got 2 nodes here. Let's just add another node just for fun. So we're going to have actually I'm going to go ahead and erase that real quick. So I'm just going to draw another node right here, like so. And we'll just give that a value of 2. And that's going to have a pointer as well. And this pointer right here is going to point to that info field. So each one of these that consists of a pointer and an info field, or an info field and an info field and a pointer, is a node. Now, the beginning and the end of a singly linked list are the head and tail. So the head is actually just a pointer. And that allows us to access the beginning of the singly linked list. So basically, remember when we were using collections, when we run the .next function for the first time, that takes us to the first value in our collection. And it's kind of that's kind of the role that the head plays. If you were to run .next, then you'd be accessing the head, which is just a pointer to the first node, so that would take you to the first node. So the head is just a pointer that takes you to the first node in your singly linked list. At the end of a singly linked list, we're going to have a tail. This one's a little weird because this isn't really lead nowhere. Like, it just has a value of null. So if you try to access this pointer, you're not really going to go anywhere. And one thing that's important to notice about singly linked lists is you can only move forward through a singly linked list. There is no way to move backwards. So once you get to the end, you're kind of just stuck. Now, that's basically what a singly linked list is. The other types of lists are circular linked lists and doubly linked lists. What we're going to do first is we're going to look at circular linked lists because I think that's probably the most similar to a singly linked list. Now, there's not a huge difference between a singly linked and a circular linked list. The singular difference is the fact that right here, where we had a tail that led nowhere, instead, the pointer on the last node is going to lead to the information field of the first node. So when we access this pointer right here, we're going to end up with at the back of the first node. So we're just basically going to keep going through the linked list again and again as many times as we want. And when we look at problems that involved, so I guess I'll write circular linked lists here. But when we work with problems that involve circular or even singly linked lists, oftentimes we're going to be told or given a position. So the problem might say, okay, you're going to start at this particular position right here. If you move two nodes forward, where are you going to end up? So we're always going to be at some position on the singly linked list, or in a linked list in general. And if you have a singly linked list, once we get to the last node, I mean, that's just going to be our position. With a circular linked list, we can keep going around and around for as many times as we want. So those are singly and circular linked lists. The next type of list we're going to look at is going to be a doubly linked list. Now, this obviously shares similarities with the other types of linked lists we just talked about. The big difference is that each node actually has 3 components. I'm just going to draw that a little bit bigger right there. We're going to have 2 nodes and an information field. So we're just going to write prev right here, and next right here, and then our piece of data, whatever that might be. We'll just say it's -2 to start out with. Now the difference between doubly linked and singly linked and circular linked lists is that you can move backwards and forwards in a doubly linked list. So we're going to draw 3 nodes right here to kind of illustrate what that looks like. Okay, so we've got 3 nodes right there. We're just going to write the prev and the next just to clarify that we're referring to pointers right here. And now I'm going to go ahead and actually draw the pointers. So we're going to start with a head as always. Okay. Or that's actually not going to go to prev. That's going to help us access the first information field right there. And that's going to be the head. Now, the next pointer in this particular node is going to access the information field on the next node, and so forth. However, we also have the previous nodes to account for. Well, actually, this one right here, we'll talk about this one right here. This one is going to be a tail. And like all tails in singly linked lists, that's going to just lead nowhere to null. However, when we get to this node, we don't have to go nowhere. We can actually just go backwards in our linked list. And we can do that using our previous pointer, right? So right here, we've got this. If we access this pointer, this is going to send us backwards to the node we were just at. And similarly on this node, if you want to go backwards, it's going to send us to the information field of the previous node. And right here, we kind of have 2 tails. So right here, if we try to go backwards from this previous node, we're just actually going to end up at null. And that is a doubly linked list. So notice the big difference between the two is the fact that we have 2 pointers on each node, and that we can move back and forth through the linked list. So now that we've kind of looked at what doubly and singly linked lists are, let's go ahead and let's talk about some of the basic tasks that you need to be able to do with all of these different lists. So this is actually on the slideshow, but I'm just going to kind of cover this briefly right here. Basically, what you need to do is be able to traverse a linked list. And that's not really, there's not really much to that. That's basically what we did here when we were talking about the position. So we're not even really going to really go through that. Basically, all you need to be able to do in order to traverse a linked list is understand how your pointers work and how you can move through the different types of linked lists. So a singly linked list, you can only move forward. With a circular, you can move back around. With a doubly linked list, you can move forward and backwards. And if you know that, that's enough to sort of traverse a linked list. You're not actually going to have to write any code for this topic. Now, the next thing we want to be able to do is to add values. So add values to a linked list. And you're actually going to have to draw a diagram and possibly annotate this process in your exam. So what we're going to do is we're basically going to go over how that works for each type of linked list in as concise a way as possible. So right here, we basically have, let's say we have a singly linked list. So you've got this right here. We've got a pointer, and we've got another node. And let's say this is just the middle of a linked list. We have another node pointing to this one, and we've got this node pointing to another one. What we want to do is we want to add a new node in between that looks something like this. Now, the way to do that is basically we're going to get rid of, not really get rid, but we're going to stop this node right here. So this node pointed from, so that pointer pointed from this node right here to the information field right here. Instead, what we're going to do is that same pointer is going to point to the information field in our new node. And the pointer from our new node is going to point to that information field right there. And that's basically how we can integrate a new node into our linked list. Now, this is probably a good opportunity to go over how to get rid of a value from a linked list as well. So let's say we've got this linked list right here as we made it with 2, 3, and 4. And let's pretend that there's actually another node that we haven't really talked about. Sorry for my awful rectangles. So let's say that has a value of -7, and that's basically what that looks like. Now we want to get rid of the node with the value of 4, so this one right here. So what we're going to do is this pointer right here should stop pointing to 4 and should point to -7. And that node is not going to point to -7 any longer. So we're getting rid of the pointer, and we're also getting rid of the pointer to that particular node, and this is just going to point to -7. So basically what we're doing is we're making the node that we want to delete an orphan. We're not pointing anything to it, and the pointer is not pointing to the node that it was previously pointing to. And this kind of works the exact same way for both for both single and circular linked lists. Now the principle remains the same for doubly linked lists, but it's slightly more complicated because of the fact that we have pointers pointing to the previous node and to the next node. So let's just take a quick look at what that looks like. So we're going to draw 2 nodes in a doubly linked list. Sorry again for my terrible drawings. I was never that great an artist. Okay, so we've got 2 nodes right here. Let's say we have -5 right here and 7 right here. And again, I'm writing pre-even next here just to highlight the roles of these particular pointers. And we want to add, so we're just going to say that this is right in the middle of a longer doubly linked list. This points to this information field right here. This points to this information field right here. And then these have their own sort of things that are pointing to them. So we want to stick a new node right in the middle right here. So of course that node is also going to have 2 pointers. So we'll have, let's say, 4, prev, and next right here. Now similar to what we did before, we're going to get rid of the existing pointers between these 2 nodes that surround the new node that we're going to insert. So we're going to erase this one. And we're going to erase this one right here. Okay. So what's going to happen is now we're going to take our new node, and the previous pointer is going to point to this information field right here. And the next node from, or the next pointer from that node is going to point to our new node right here. And then with our node that contains the value of 7, the previous node, or the previous pointer, is going to point to our new node. And the next pointer from our new node is going to point to the information field of that particular node. And that's basically how we add a node to a doubly linked list. If we were to delete the node from this list, so let's say, for example, we have we'll do an example that's, well, actually, let's say we want to get rid of this node now. So we have this node with the value 4, and we want to get rid of it. What we're going to do again is we're going to make it an orphan, as we did before. It sounds terrible, but we're going to get rid of all the pointers from it to the other nodes. Okay? And then we're just going to reconstitute those pointers, or constitute those pointers between the nodes that are now going to be next to each other. So this is going to go back to pointing right here. This pointer is going to go back to pointing right here. And I think that's actually pretty much it. Yeah, that's about it. So that's basically adding and deleting to a doubly linked list. Now I went through those because you do need to understand, you need to be able to illustrate that particular process. So we went over how to traverse a linked list, how to insert values, not from a linked list, but into a linked list, and then how to remove values from a linked list. Those are the basic things you need to be able to do with a linked list. And again, this is mainly going to be like you illustrating these processes, just because you're not going to be required to write any code. The most that I've ever seen in terms of code with a linked list is something that looks like this, which is telling a pointer to take us to the next node. Strangely, it's not even a function. It's more like an attribute. I don't really even know why they do that. But, well, actually, I do know why they do that. But I wouldn't worry about that. I've only seen it once in all the exams that have been given so far in this curriculum. So let's move on to some practice questions. So right here we have a very typical linked list problem. It says a network is set up with shared printers so that when a user wishes to print jobs are sent to a queue until the printer is available. So this actually combines a bunch of different data structures, which is why I think it is a great problem. So right here it says outline why a queue is the appropriate data structure to manage print jobs. Now, simply we can just say that it is the appropriate data structure because of the fact that if you send a print job to a queue, so let's say you're sending print job 1 to a queue. That's going to be the first thing that's going to be processed. Then print job 2 is going to go behind that, which will make it the second thing to be printed. And then the next print job will go behind that. So really, like the first person to print, their job is going to get handled first. And then the second person and the third person, which makes a lot of sense. It's the last in, first out scheme. As opposed to a stack, where the most recently submitted print job would be the first one to print, which really just would not be fair at all. So just looking forward at C, if we put our print jobs into a stack, we would put 1 in, and then 2 in, and then 3 in, and then we would pop those out. So that means that the third job put in, the most recently put in job, would be the first one to be printed, and then the second. So the most recently put place job would be the one to be printed first, and then we would get to the older jobs after that. Which doesn't make sense because if you're the first one to print, that means that your job would be the last one to be printed out. And if new jobs keep getting added to the stack, that means that you probably actually never see a print job. So that's why a queue would be better than a stack. But then if we look at B right here, it says draw a diagram to show how a print queue may be implemented using a linked list. So basically what we're doing right here is we're just drawing a diagram of a linked list. So it doesn't really say what type of linked list. That could happen in other questions, but we can just assume that we're going to have a node. And we could just say print job pj1 with a head that's pointing to it. And then we're going to point to pj2. And then that's going to point to pj3, for example. And then that's going to point to we're just going to have a tail that's going to point to null. Because when you're done, you're pretty much done if you don't have any print jobs left. But in this case, we would continually just be adding print jobs to our linked list. So ideally, you would never really run out of print jobs. But even if you did and you just had a new print job, then you just add that to the head that would be left over. But anyways, that's not as important. Really, this diagram is important. And this is my diagram. Let's go and look at the mark scheme and see what they have right there. So as you can see right here, we've got a head. We've got our head. We've got our tail. They had the tail as just the last node. Either one is fine. As long as you had tail somewhere in this last node, that kind of works. They also labeled the pointers. And they kind of had the pointers in between between the nodes drawn just the same way as we would. And right here, just looking at the mark scheme, it says correct use of pointers and null pointer in the last node. So we have to have this external pointer to the beginning of the list, head, external pointer to the end of the list, tail. So again, even if you had like tail right here, as we did before, that would still be correct. Honestly, online, when I looked this up, I saw the tail referring both to this pointer and to the last node. Similarly, and that's similarly true with the head. But I mean, if you're going to write it here either way, I mean, it's going to be correct. And then each node consists of at least two parts fields, the data and the pointer. And the data is what we referred to as the information field in our previous example. So I guess the biggest takeaway from this is just basically like how a question like this would look on the exam. And then also the slight ambiguity in terms of like head and tail. Okay, guys. So now let's take a look at binary search trees. Now, before we get started with this, I just want to let you know that I'm only doing about 1 or 2 practice questions for each of these topics, just because I want to keep these videos as short and concise as possible. If you want to see some of the other practice questions, you can look at the link to I'm just going to put out a slideshow full of the questions, and it's going to be linked in the description. That being said, let's get started with binary search trees. Now, there's a few basic tasks that we need to be able to complete with binary search trees. We're going to build a binary tree from a set of integers or letters. Traverse means just go through a binary tree in a certain order. And there's 3 particular orders we can go through a binary search tree in. We're going to learn how to add new values to a binary tree and then remove existing values from a binary tree and then rebalance that tree. So I'm basically going to explain like, okay, what is a binary tree? We're going to build one, and then I'm going to conduct these different operations on that same binary tree so you have a clear example of how this concept works. Okay, so let's pretend that we have a set of values that we want to put into a binary tree. Now this is actually called a binary tree in the IB exam, but in reality, if you want to Google online and actually find this concept, you're going to have to type in binary search tree, because that is specifically what we're referring to. A tree that we can use to handle searches in a more efficient way. So what we're going to do is we're going to start by building a binary tree. So we're going to use a set of data. So 50, 17, 12, 72, 19, 54, 21, and then 79. Now, your binary trees are generally going to have integer numbers, but in the IB exam, you might also have letters, so it might look something like B, C, E, D. But all that means is that these numbers are going to correspond to integers, for example. If you have names, we're going to go in alphabetical order. And I'll show you an example of that afterwards as well. But right now, let's just focus on a binary tree involving integers. So what we're going to do when we construct a binary tree is we're going to start with the first value and then work our way to the subsequent values. So first we're going to write a 50. Now that we've written 50, what we need to do is we need to look at our next number, which is 17. And we need to decide, is 17 greater or less than 50? And we know 17 is less than 50, so that means that it's going to go on the left side of 50. So what we're going to do basically is we're going to end up with a tree of values where everything on one half is less than 50 and everything on the other half is greater than 50. So we put 17 on the left of 50. Our next value is 12. Now 12 is less than 50, so we know it's going to go on the side with 17. So we're going to look at the next value in our tree, which is 17. We're going to see, is 12 greater than or less than 17? And it's less than 17. So it's also going to go on the left of 17. Now our next value is 72, which is greater than 50. So that means it's going to go to the right of 50. That's going to be the first value to the right of 50. So we're going to have 72 right there. Now our next value is 19. So 19 means we're going to have to go back to the other side of the tree. So we're going to go to 50, and then we're going to go down to our first node in this tree. Because this is really actually all of these lines I'm drawing are pointers to different nodes in this tree. So we're going to go to 17, and we're going to see, okay, is 19 greater than or less than 17? It's greater than 17, so we can draw a 19 right here. Our next value is 54, which is greater than 50. So we're going to go to the right side, and we're going to go down to our first node, 72. We're going to check, is 54 greater than or less than 72? It's less than 72, so we're going to draw it right there like that. Our next value is 21. So we're going to look at our tree, and it's less than 50, so this is going to go on the right side, or sorry, the left side of our tree. So we're going to go to 17. Basically each node here can only have 2 leaves. These being called leaves. This is actually our root node right here. So this is our root, and these are leaves. Now, each leaf can only have 2 leaves, can only have 2 other leaves on it. So we're going to look at 17, and we've got 2 values that we can work with right here. We've got 12 and we've got 19. Now right here, we know that we basically need to look at 17. And the idea is, even right here, we want to have all the values that are greater than 17 on this side, all the values that are less than 17 on this side right here. So that means that 21 is greater than 17, so we're going to have to go down to 19, to our node on this side right here. And we're going to check, is 21 greater than or less than 19? Now 21 is greater than 19, so it's going to go right here. Next we have 79. So we're going to go down to this node right here, and we're going to see, is 79 greater than or less than 72? And it's greater than 72, so it's going to go right here. So it's a really basic example of how to create a binary tree. What I'm going to do right now is just go through another example, just because otherwise it may not be clear at all. One thing I want to clarify about binary trees as well is the fact that there's no duplicates. So you're just going to have a bunch of unique values. So that being said, let's go ahead and let's just make up another set of numbers. So let's say we have like 7, 9, 3, 12, 15, 4, 5, and let's say we've got 8 and 17. So it's kind of a big one. We're going to start with 7. Okay. We're going to look at our next value, which is 9. Is that bigger or less than 7? It's bigger, so we're going to draw it right there. We're going to look at our next value, which is 3. Is that bigger or less than 3? It's less, or is that bigger or less than 7? 3 is less than 7, so we're going to go right there. Now we're going to look at 12. Is that bigger than 7 or less than 7? It is bigger than 7. So it's going to go on the right side, and we're going to go down to 9. Is 12 bigger than or less than 9? It's bigger, so it's going to go there. Next, we're going to look at 15. Okay, so 15 is greater than 7, so it's going to go on the right side. And we're going to go to 9, and 15 is actually greater than 9, so it can't really go on the left side of 9. So we need to go down to 12. We need to see, is 15 greater than or less than 12? And it is greater than 12, so it's going to look something like that. Now we've got 4. So what we can do right here is we're going to go to the left side, because 4 is less than 7. We're going to go to 3. 4 is greater than 3, so we're going to go right there. And next you've got 5. 5 is also less than 7. So we're going to go to 3. And 5 can't go on the left of 3 because 5 is bigger than 3. So we're going to go down to 4, and 5 is greater than 4, so we're going to draw 5 right there. Next, we've got 8. 8 is greater than 7, so it's going to go on the right. So we're going to go down to 9. And actually right here, 8 is less than 9, so we can fill in this spot right here. Then we've got 17. So this one's a tricky one. We're going to go, obviously, to the right again. We're going to go to 9. 17 is greater than 9, but it can't go here. It's also greater than 12, but it can't go right here. So we're actually going to end up with 17 on this side right here. So that's another quick example of how to draw a binary tree. Now, what I want to talk about let's go back to this example right here, is what happens if we want to remove a value. So let's say that we decide that we want to remove 72, okay? So we're just going to get rid of this one right here. So what we need to do at this point is we need to actually rebalance the tree with the values that are existing. Now, nothing is going to change. So basically what we're left with on this side is we have this empty space, and we got 54 and 79. Both of these are greater than 50, so they are going to stay on the right side of the tree. However, we need to reconfigure these to reflect the current reality. So right here, we're going to have, so 54, both 54 and 50 are, or both 54 and 79 are greater than 50. And there can be multiple configurations to this tree. There's actually not really a single right answer. But the way that I'm going to do it is I'm going to have 54. And then I'm going to have 79 right there. That way the tree is still balanced and still following all of the necessary rules for a binary search tree. Let's go ahead and let's remove a value from this one as well. Let's say we want to get rid of, let's say we want to get rid of 12. Get rid of this as well. We've got 9 here, we've got 8 here. We need to reflect the current reality. So we're actually going to look at, and again, all of these values on the, whatever's left over on the right is still greater than 7. So we're not going to be moving things from one side to the other. But what we are going to do is we're going to move the 15 up here, because that's where that belongs, right? And then the 17, I'll just go and erase all this. The 17 is going to go right underneath that. Again, there is more than one way to do this, but what's important is that we need to follow the rules, and then we will inevitably have a correct answer. So that's actually what happens when we delete values. If you want to add a value, it's actually not any different than just building a binary tree. So let's say, for example, we want to add 29, or let's make it even more interesting. Let's say we want to add 6 right here, or actually 2. Let's say we want to add 2. We just look at our binary tree and we just kind of see where it fits in. So we know that 2 is less than 7, so it's going to be on the left side. So we're going to go to our next node, which is 3. 2 is less than 3, so it's just going to go right here. There's a spot right there that's already made for it. What I want to draw your attention back to again is this particular subtree right here. Now, what was interesting about this tree is that we actually had to go down to 17. So this is actually, like, particularly when we're adding 21, we had to go down to 17, and we had to decide where we wanted to add 21. Now, what's important is that for every subtree that we have, for example, right here, with 17, we have a subtree that is a smaller tree inside the greater tree. And it basically needs to follow the same rules as the big tree in general. So the big tree, we know that values that are greater than 50 need to go on the on the right, and values that are greater than or less than 50 need to go on the left. Similarly, right here, we know that values that are greater than 17 need to go on the right, and values that are less than 17 need to go on the left. And then once we know that, then we can then we can kind of figure out pretty easily where to put the existing value. So now that we've done that, what I want to go over is how to traverse binary trees. Now to do that, I'm just going to redraw. So we've got 7, 3, 2. We've got 4 right there. We've got 5 right there. Then we had 9, 15, 17. So basically what we have 3 ways in which to traverse or go through a binary tree. We have preorder, in order, and post order. And I'm going to draw a little like figure right here that looks like this, and it's going to make sense in a second as to why I'm doing that. So in order to figure out what order to traverse this binary tree using preorder, we're going to draw a little thing, I don't know, like a stick from each one right there. It looks like that. Okay. And what we're going to do is we're going to start on the left side, and we're going to draw a line through each of those sticks. It looks like this. So we're going to start right here. We're going to start at the top left, let's say, the top left. And we're going to start there. We're going to go down. We're going to go to the next one right here on this side, and then that one right there. And then we're going to go to the top left right here, go down. And then we're going to go back around and go to the top leftmost right here. And then we're going to keep going like that. So that means that our pre-order order or sequence is going to be 7, 3, 2, 4, 5, 9, 15, and 17. And that's simply accomplished by basically drawing this little stick with a dot and then drawing a line through it. Always staying at the top left, so the top leftmost element. Now, if we look at in order right here with the same binary tree, let's say we have 7, 3, 2. So basically the same binary tree we worked with before. We're going to do the same thing, but we're actually going to draw our stick with a dot. I don't even know what to call it, but downwards. So it's going to look something like this. So again, what we're going to do is we're going to start with the top leftmost element, which in this case is actually number 2 right here. So we're going to start there. We're going to draw a line like that. We're going to go back up like that. And that's it. So that means that if we're using Inorder Traversal, our sequence is going to be 2, 3, 4, 5, 7, 9, 15, and 17. And finally, we're going to talk about post order, which actually just follows the same. So I'll just write in order here to clarify that. But post order actually follows the same sort of logic. 7, 3, 2, 4, 5. Then we've got 9, 15, and 17. Now with in order, rather than having the stick off to the left or at the bottom, it's going to be off to the right. So it's going to look something like that. One thing to remember is that the pointers between the nodes act as sort of boundaries. So again, we're going to start at, this one is a bit weird. We're going to start at 2. And there's really nowhere to go. So we're going to have to go to 5 right here. And then up to 4 and then 3. And then we're actually going to have to go all the way back here. And then up to 17, 15, 9, and 7. Now normally we would normally I told you guys that we're going to go order from the top left. But in this case, we actually are going to hit, generally we're going to hit every element that we get to first. And so for example, we're not going to go from 2 to 3 and then back around. So in that case, we have no choice but to go to 5 and then 4 and then 3 and then 17, 15 and then 7 being last. This one, post order, this one's a bit different, but still I would say the same logic applies. If you look at any of these, we're starting at, I would still say we're starting at the top left element, the one that's most to the top left, which even number 2 is in this case, even if it doesn't look like it. And then we're trying to go to the top leftmost element, but the thing is we can't skip around. So in that case, we're going to have to go to 5 and then 4 and then 3, even though those are technically not the topmost. But if we were to do anything else, then we'd have gaps and we'd be going in weird loops. So that's going to be, the sequence isn't going to end up being 2, 5, 4, 3, 17, 15, 9, and 7. It's going to be post order. So it's pretty straightforward. You just need to remember preorder. So preorder is going to be to the left, in order is going to be in the middle, and post order is going to be to the right. So pre, in, and then post. And really, this is just going to be a question in the IB exam, where you literally just need to write the sequence in which a binary tree is traversed according to either preorder, in order, or post order. Now, the last thing I want to go over is kind of just going back to binary trees, and that's what happens if we get rid of the root element. So this is sort of a more complex case because of the fact that a lot of stuff kind of has to change. So if we're getting rid of the root element, we need to actually rebalance the whole tree. And this sort of idea of balancing a tree is kind of fundamental to binary search trees in general. Just because of the fact that it's kind of built around everything to the right of a particular node, or everything to the left or right of a particular node being greater, everything to the right of a particular node being greater, regardless of where you're actually at in the binary tree. So let's think about it. What if we just get rid of, or actually probably better off, what if we get rid of 50 right up here? So you got this one right here. Okay, and what if we just get rid of that? Now, what we need to think about is what element we're going to put in the middle, such that everything to the right is less than, and everything to the left is greater than. And honestly, there's not a right answer. I would say that whatever you do, you're going to have to make sure that the same logic applies, where everything to the right of that element is greater, everything to the left of that element is less. So how I would handle this situation in this case is going to be, I would just take 54, put it right here. I just put that right there, and I end up with 54, 17, 12, this one we're going to have 19, 21, and 79. And that would be a valid answer. Now going back to this concept of balancing, the biggest advantage of a binary tree is that you can go, if let's say you want to find the number 12, for example, okay, let's say we want to find 12. You can go down to 54, and then you can immediately compare it to that node. And then you can go to 17 and compare it to that node, and very quickly you're going to get to your answer. Versus if you just had an array that looked like this, you'd literally have to go through every single element before you could check whether 12 was there, okay? So of course you get there pretty quick on the fourth element, but if it was all the way at the end, it would take you a lot more time. And so with a binary tree, you're effectively cutting in half the amount of time that is required, or actually even less than half, the amount of time that's required for you to find a particular element. And that is what is special about a binary search tree. Now, that's kind of it for binary search trees. I've been kind of rambling along. I hope you guys are able to follow along. Before we go into a practice question, what I want to talk about, or we're going to look at the advantages and disadvantages and then go into a practice question. What I want to talk about real quick is in the case where you have letters. So if you have a sequence of letters like this, so if you have B, C, E, D, F, or if they're in alphabetical order, what you're basically going to do is just give them numbers. So if they're letters, you can just say, okay, this is the second letter, this is the third letter, this is the fifth letter, this is the fourth letter, this is the sixth letter. A, B, C, D, E, F, G, yeah. So, okay. Anyways, so just based on that, you can decide how to place them in the tree. If you have names, if you have like Amit, John, Lisa, whatever, you're basically going to have to compare them to each other to see where they fall relative to each other in alphabetical order. It's the same way that we compare numbers here to see whether they're greater than or less than each other. A name that has a letter that's further down the line is probably going to be to the right of Amit, and Lisa is probably going to be to the right of John. So that's just something you should be aware of. You may see that on the IB exam, where you need to work with strings or with letters rather than integers, but essentially the same concepts apply. So that being said, let's go ahead and let's look at some of the advantages and disadvantages of binary search trees. Okay, so here are the pros and cons. So one of the big advantages, as we talked about before with binary search trees, is that searching is time efficient. Only half the time is needed to find a particular element. Moreover, elements don't need to be removed to be checked like stacks or queues. So with stacks or queues, you need to do either pop or .dq to see what's in there, to actually be able to access and see what's in those particular data structures. With trees, it's kind of like arrays in the sense that you don't really need to run a specific function. You can just go into the tree and just start navigating through elements. The disadvantage is that a binary search tree needs to be balanced. So this means that when you delete or when you insert elements, you need to rebalance that tree to make sure it follows that principle of the higher value being on the right and the lower value being on the left. And this can be computationally intensive and requires some code to do. Also, searching is slower than arrays in cases where the location is known. So if you want to find a particular number in an array and you know that it's at index 4, it's pretty fast. You just go to that index. But you can't access values based on indices in a binary search tree. Regardless, you'd have to go through the whole binary search tree until you find that particular value, which is why searching can be slower searching can be slower in binary trees than arrays where the location is known, because you still need to go through the tree regardless. Now let's move on to a practice question. Okay, so let's take a look at a practice question. I'm kind of going to ignore these for right now because what I want to do is I want to focus on the binary tree stuff. So we're going to look at this right here. Consider the following binary tree. An in-order traversal of this binary tree will produce a list of names sorted in ascending order. State the result of Postorder Traversal. So this is kind of weird. Like, I don't really know why this is relevant. But what I do know is right here we have a tree. And this tree looks something like this. We've got hazel, elder, and then elm. And don't worry about where like these arrows are pointing, whether they're pointing to null or whatever. This tree right here that I'm drawing is what this means. And then we've got larch, holly, and rowan right here. That's getting kind of cut off. So in this problem, we have two different tasks. It says state the result of Postorder Traversal, and then draw the binary tree after deleting the root node, this being the root node right here. So what I'm going to do is I'm actually going to copy this tree into a different app right here, just so we have more space to work with it. Okay, so I've got this right here, and we've got two tasks. We need to find the Postorder Traversal. Let's say the Postorder Traversal sequence. And the next thing we need to do is we need to delete the root node and then just see what happens, basically. So let's start with this one. So remember pre, in, post. So with post, we're going to draw our little stick right there like that. That's going to look like that right there. It's pretty ugly, and that's going to look like that. So remember, we're generally starting at the top leftmost point, but keeping in mind that we cannot cross our pointers. So that means that elm is going to be the one that we start with. This is the leftmost that we can access coming from that point right there. Okay. So we're going to draw it through here like that, and we can't do anything else. So we're going to have to go in here. Then we can go like that up here. So that means that our order is just going to be elder, elm, holly, rowan, larch, and then hazel. Now, the next thing we need to do is we need to delete the root node and see what happens. So that basically means getting rid of Hazel and putting something else in there. I mean, there are a couple of ways to do this. I think that the main idea is that you want the tree to be as balanced as possible. Now, this means you try to get as close to having an equal number of elements on the left side and the right side, and that's just so that you can you just have more of a chance of finding the element that you want, just using the binary search method by seeing what's higher on the left and then the right, and then going in that direction. So you want this to be as balanced as possible. So you want to choose one of the values in the tree that's going to be probably the most in the middle of all of the others. And I think just based on looking at the alphabet, that would probably be Holly. Like any of these would really work, but I would choose Holly. We're getting rid of Hazel, and we're going to put Holly in there. Hazel's gone forever, but Holly is going to be in there, and that's basically the way that's going to look. So let's go to the mark scheme and let's see whether we did it right. So it does look like we got the order right for the post order, and also we put Holly right here. And so that seemed to work. I guess the other alternative would be Elm, because Elm would be another one that would be kind of as much in the middle as possible, allow us to strike the best balance between both sides, the left and the right side. But I would argue that Holly would be the best, because essentially we'd have the same order. We're just moving one particular element or node in the tree. So what I want to highlight from this question is something I didn't mention before with balancing binary search trees, which is the fact that you really do want to optimize the binary search tree such that you have as equal a number of elements on the right and left as possible, because that's where binary search trees essentially hold their advantage in terms of allowing us to quickly find values. So actually, that's it for this video right here. If you want to see more practice questions, you can check the link in the description. If you want a compact way to review these concepts, feel free to click on the link in the description below and purchase one of the HL study guides. That being said, if you found value in this video, please remember to like and subscribe to the channel. Also join the Discord if you have any questions. Have a nice day.